of data, and they want very, very fast response to uh, response to signals. So that is why they used gallium arsenide, in these computers. But these are very, very expensive computers because gallium arsenide is very, very expensive to make. And so you see also, mobilities in some compounds, some other compound semiconductors, and you see how they vary. Okay, so now we can say that the drift velocity, now we're specifying the velocity, the average velocity, as the drift velocity. Why? Because the mechanism is drift, because we have an electric field. So the drift velocity of electrons in an electric field can now be written as mu n, okay, times E. Okay, that is the drift velocity in an electric field for electrons is of this order, and of course we have a minus sign because it goes opposite to the electric field, and the drift velocity for holes is also mu p times E, okay, where E is the electric field. Okay, so the mobility is a very important factor, and now we know what the mobility is. Mobility is E times tau divided by m star, and it is true for both electrons and holes. Okay, so now if we have this expression, now what we will do is we will go back and to this here. Okay, we'll clean it up maybe. We'll go back to these equations here. And in this equation, we have Vn now. So we'll have to put Vn here or Vp here and get the current density and for electrons and for holes. And so this will be the current densities coming from the drift mechanism or from an applied electric field. Okay? So we can immediately come up with these expressions, and again, mu is not showing up here, and this would be another parameter here. So if you look here, what you have is E n mu n E. So I ignored the minus sign here because I'm only looking at the magnitude of the current. I'm not looking at the direction. So the magnitude of the current by electrons is E, the electronic charge, because remember, we know that J for electrons, Jn, we found it, from that box example is E n Vn. Okay, so if we ignore the minus sign, and just think about the magnitude of the current, this is my E, this is my N, and instead of Vn, I have mu Ne. Okay, so that is my expression for the current density from electrons. So now what I did is I used this sigma sub n, n for electrons, and I wrote it instead of E times n times mu n. So this sigma n, which is the electronic charge E, times the density of free electrons n times mu n is conductivity. Conductivity component contributed by electrons. Now you hear the word conductivity, okay? And this conductivity depends on the density of electrons, free electrons, and the mobility of these free electrons. A product of the density and mobility times the electronic charge. Similarly, the current diffusion, the drift current from holes, mu, is given as Jp, again in terms of a conductivity, sigma p, and this conductivity sigma p is, this is wrong here, this is p. So you might want to correct this. So this is p again. That's the density of holes. Okay, so these are the expressions. So the the drift current of holes is E times P. P is the density of holes, the free holes in the valence band, times mu P, which is mobility of holes. E is equal to sigma P times E. Now sigma P is the conductivity component contributed by holes. So we have conductivity from holes and conductivity from electrons. Okay, so this is again Jp is the drift current density by holes. So now we have all the gradients. We have developed this. These are the current densities in any piece of semiconductor. How do we make it? Okay, how do we make this piece of semiconductor? We start, say, with the p-type substrate here, and then we use a mask. That's the top. Well, this is the top view. We have some openings, and what we do here is we have a N region. So we have a p-type substrate, p-type silicon, P. Then we do a mask and we do ion implantation with N-type dopants like phosphorus. So we make this N-type region. And then we do openings, do some oxide here, okay. And then we have openings, and then we have metal, okay, connecting to the N side, and another metal here connecting to the N side, okay. So we have an N-type resistor. And this metal is a special metal, treated in a special way so that we have what we call ohmic contacts. We're not going to talk about it now. We'll talk about it later. But anyway, these are the two contacts to the resistor. And this part here is our resistor, this dashed part. This is N-type resistor put in a P-type substrate. So N-type meaning that we engineered it in such a way that we dope it with phosphorus, and so N is equal to the number of dopants. We saw that for an N-type, the number of dopants determine the free concentration of electrons. Okay? And we see from our electrical engineering studies that the IV characteristics on a resistor is linear. I is linearly dependent on V, as you can see here. And the symbol in electrical engineering, the symbol for a resistor is this zigzag line. So the characteristics, the IV characteristics of a resistor is a straight line. IV are linearly dependent on one another. And the symbol that we use for a resistor is this zigzag. Okay? And now, just take you back to our expressions. Remember, the current, total current, is the current density times the area. Now, the current density in a drift is En mu n times E. That's what we obtained in the previous slides, times the area. So this part here is the current density, Jn, and if you have N-type, so Jn, and this is the area, cross-sectional area. So that would be, again, we have mu n here missing, okay, that would be the current I equals E, electronic charge, times N times mu n. And now, if you have a linear resistor, okay, and if you have, okay, a voltage applied, which is V, okay, between these two terminals, then the electric field, you remember we have Poisson equation in electromagnetics, the electric field relates to the voltage in a linear resistor by V over L. That is to say, the length of the resistor is L. So the electric field coming from a voltage V is E equals V over L. So instead of E here, we're going to substitute V over L, then times A. Okay, so that is E equals V over R. So I, the current, is equal to all of this, okay, here, times the voltage. So all of this here is what we call the inverse of the resistance. So the resistance will be L over A divided by E N mu N. So this is what we call the resistance, right? So this tells us that I and V are linearly dependent on one another. This dependent or the slope of the dependence is called the resistor, or in other words, V is equal to IR, Ohm's law, okay, which is this linear relationship that we see between I and V. Now you can clearly see that the resistance R, which is the slope of the IV curve, okay, comes from the electronic charge, comes from the charge density, the free electron density and free holes density, and comes from mu n, which is the mobility of electrons, okay? And then also this is a geometric factor, which is area and length, okay? So V is equal to IR, okay? So if we go further, we can come up with more relations. En, and this one, mu p, we can write this as sigma, right? So the conductivity, remember, we have sigma n, the conductivity of coming from holes, sigma n, and the conductivity sigma b coming from electrons and from holes. We add them. These are the total gives us the total conductivity of the resistor, okay? And we know that 1 over sigma, 1 over the conductivity, equals to the resistivity, rho. So the resistivity rho is actually this here, okay? So it depends on the mobility, it depends on the free carrier concentration, electrons and holes. So you can see that we can always engineer the resistor, engineering it, controlling sigma, the conductivity, and the same way controlling the resistivity. How? By controlling the doping N or the doping P. So if we engineer the doping N and P, we can engineer the conductivity and we can engineer the resistivity. So we can make resistivities from 0.1 ohm centimeter all the way to 100 mega ohm centimeters. So we have all this range to vary the resistance and have different circuit functionalities. Okay? So that is what's beautiful about a semiconductor, is you can tune the resistance in a resistor, a semiconductor resistor. You can engineer it by engineering the number of dopants that you put in a semiconductor. Typically here for silicon as a semiconductor, look at the resistivity when it's intrinsic at room temperature. It's 5 times 10 to minus 6 ohm minus 1 centimeter minus 1. That's the conductivity. But look at copper, which is a metal. It's 6 times 10 to 5. So it's 11 orders of magnitude higher in conductivity than the semiconductor, intrinsic semiconductor. Okay, look at silicon dioxide, which is an insulator. Okay, the difference is between the silicon dioxide and the semiconductor are 10 orders of magnitude. So the difference here between these two is 21 orders of magnitude. So we have, very high conductivity in the case of copper or metals, very small conductivity in the case of insulators, but in the middle you have semiconductors, and you can push the conductivity of the semiconductors up when you do doping, okay, and you make it as close as possible to metals, by doping it N-type and P-type. This is a problem here which we will do, okay? And in this problem, electrons are injected into one end of a 1.5 micrometer long semiconductor. So the length L is 1.5 micrometer and are found to require a transit time of 10 minus 2 seconds. So it takes them 10 minus 2 seconds to reach the opposite end. So they come into a semiconductor, go 1.5 micrometer inside the semiconductor and get out at the other end in 10 to minus 2 seconds. That happening at room temperature. When the sample is subjected to a voltage of 0.1 microvolts, what is the electron drift velocity and the electron mobility of this semiconductor? So now, the average drift velocity of electrons Vn is equal to the length traveled over the time. That gives me the average velocity. So Vn is equal to length L over the time t. So if we substitute for the length L, 1.5 times 10 to minus 4 centimeters. So 1 micron is 10 to minus 4 centimeter. Okay, so if we substitute that, okay, for the length here, and then if we substitute for time 10 to minus 2 seconds, then we get an average velocity of 1.5 times 10 to minus 2 centimeters per second. So the drift velocity is Vn times, here you should have mu n, right? So this is how they're related. So now we know the drift velocity, and if we know the electric field that is applied, look, here a voltage applied is 0.1 microvolts. So let's go here and determine the mobility. Okay, the mobility mu n is actually from this equation here. Mobility mu n is just Vn divided by E. So it's Vn divided by E. Now what do we have? We have Vn. Do we have E? E is V over L. I have V is 0.1 microvolts and I have L as 1.5 micrometers. So my mu n is going to be V over E. So V over E is like Vn times L over capital V, which is the voltage. So Vn is 1.5 times 10 to minus 2 centimeter per second. L is 1.5 over 10 to minus 4, and then 0.1 times 10 to minus 6. That gives you 22.5 volt minus 1.
Hello? Hello? Hello?